more often than not, especially in our implementation, in our case of machine learning, we will observe multiple random variables at the same time. Not only observe, we will want to calculate, evaluate, guess one from the other in machine learning. So that's the basic definition of our job, and therefore we need to have an understanding of how multiple random things coexist. So that's why we have a definition of joint distributions. So here, let me put the title. Joint distributions. Imagine a scenario in which we have x's, and the probability of these x's being, it's simplistic, 1 or 0, but at the same time, with some certain probability, we can observe a random variable y as well at the same time. And it just so happens that the probability that x being 0 and x being 1 at the same time, y being 0 and y being 1, it can so happen that they can be not so independent. I will introduce this particular term in a second, but bear with me. We can observe a scenario in which both of x and y can have probability of half, and it can so happen that when x is 1, y can be 1 at the same time with 1/4 probability, and this can be also 1/4, and this leaves us nothing but a scenario in which we have to allocate a 0 probability for x1, y0. So such a probability distribution in which we are talking about multiple random variables at the same time, and their joint distributions can be represented with, again, the same distribution function, right, p, but this time instead of writing px, I write pxy, because I'm talking about the joint distribution. So now I'm describing something like x and y. So it's a two-dimensional distribution, multivariate distribution, and I can have x and y vary at the same time. So for discrete case, this can be described as probability of x is equal to x and y is equal to y. And let me put star here, so this is for discrete only. And so this term, this representation, is referred to as the joint distribution of x and y. So from here, if we would like to have a distribution of p of x, all we need to look at the x-axis. So for this, I need to just remove the gravity, and let's let these guys fall on the ground, and now p of x will directly look like for x being 0 and 1. So this is only 1. So my the total probability that x can be 0 is 3/4. This is 1/4 plus 1/2, and x being 1 is 1/4. So what I did here is I did probability of x over x can be obtained from the joint distribution by what I did. I summed over y, all possible values of y, and I used the joint distribution of p of x y. So, and similarly, let me type the same thing for y as well. Probability of y given y. So if I sum over all possible x's and the joint distribution of p of x and y, I get the marginal distributions, right? So there's the term for this is marginalization. So these guys are called marginal distributions, mostly obtained from joint distribution. Similarly, for continuous random variables, we can get p of x from marginalizing over y, p of xy. This time I'm gonna marginalize over dy, right? So from minus infinity to infinity. And similarly, p of yy is equal to minus infinity to infinity parallel to xy dx, right? So if I marginalize over the axis, I just make it disappear. So this is marginalization and joint probability. And for continuous random variables, obviously the table that you see here, imagine it being continuous. So like obviously I cannot write, let me write here for continuous random variables, the joint will look like, again, in the same space, x and y space, and imagine this x and y space to be continuous and going all together. So I will need your imagination to understand that it looks like a mountain that's coming to you. The probabilities, there will be some high regions and low regions. So I'm gonna try to draw something like the mountain drawings that we're accustomed to from geography, right? So you see that at this point, the joint distribution of x and y happening is larger than everywhere else, right? So when we look at this, we can have an understanding of how the two random variables can have a multivariate distribution. So one thing that I would like to introduce in this video, one other thing that I would like to introduce is the topic of conditional probability. So if we look at this joint distribution, right? So this is for let's say this is p of xy for this discrete random variable. And if I tell you that I know for some reason that x is equal to 1, then what is the probability of y is equal to 1? Let me go ahead and draw this joint distribution here again, because I will talk about it again. So x and y, so I have this 0 1 0 1, and this was 1/2, this was 1/4, this is 1/4, and this was 0. So if I talk about what is the probability of y is equal to 1, probability of y is equal to 1, if I know, given, so this is how it's pronounced, given x is equal to 1. So this is pronounced given. And I know, since I know x is equal to 1, I directly eliminate the region where x is not equal to 1. So my region all of a sudden is this region. So I can have 1/4 of probability that y is also 1, and 0 probability that y is 0 when I know x is equal to 1. So I can then calculate the conditional probability where probability of x is equal to 1 and y is equal to 1, but now I need to normalize by the fact that probability of x is equal to 1. So I know that x is equal to 1. And the probability that x is equal to 1 is already 1/4. And the joint distribution is also 1/4 for x1, y1. So I get this to be 1. So the definition of conditional probability, which is going to be very important for understanding Bayesian Bayesian inference, is probability of x given y. So this is how the conditional probability is defined, is obtained with probability of xy divided by probability of y, because I know this is already given, and so my space is no longer the whole space. My space is now shrunk into the position that y is given, right? So this is the definition of conditional probability.